Okay, this is probably the most important video I'll make this year about wire antennas. And by the end of it, you'll understand exactly why long-haul DX does or doesn't appear in your logbook very often. So this is a standalone piece of work. It's not a soundbite. It's the whole story of what is actually happening and what your antenna is doing from everything I've learned over 25 years. My name's Callum, call sign M0MCX. I've been tinkering with antennas for years. My life literally depends on understanding what works and what doesn't work when it comes to ham radio antennas, because I make my living from them. So I want to be really clear about what we're doing today. This is not about finding the best antenna. It's about understanding what actually changes when we alter the height, the length, the geometry, various sizes. Every antenna we're going to look at, verticals, dipoles, loops, and more, are perfectly usable on air. The rules today is that they can all be easily matched to 50 ohms. They're all coax-fed. They're all efficient enough, okay? So we don't need to question efficiency, because that's not the argument. So what I want to do is isolate radiation angle, okay? And when we talk about DX, we need to understand that signals don't arrive at one neat angle. Long-haul HF energy typically arrives over a range. Now, roughly, that's between 3 and maybe 15 degrees above the horizon. And that's not opinion, okay? That's been measured for decades by military, commercial, broadcast services. And there are published tables and studies that maps the takeoff angle versus distance, and they broadly agree, and they use fancy gear to do all that. Long-haul HF arrives low, typically single-digit degrees. This depends on frequency, band conditions, time of day, a whole host of variables, but they generally arrive low, right? But rather than argue over the tables, I'm going to show what happens when antennas can't produce energy down low. Now, almost any antenna can produce fairly good RF energy at, say, 15 or 20 degrees. That's really easy. Low angle radiation is hard, and that's exactly why this analysis matters. Yes, there's also the argument for high angle skywave NVIS antennas too, and that's easy. And we'll cover it, but let's go low to start with. Now, to do this, I'm using a piece of free software. It's called MMANA-GAL. You look it up on the internet. It's not magic. It's basic electromagnetic maths, and it's based around a well-known mathematical formula called the method of moments, which ultimately comes from Maxwell's equations, right? But what I'm saying is that these models are going to be good enough, trusted enough to give us a fair indication of what's really happening. The absolute numbers aren't what matter. What matters is how those numbers change when we alter one thing at a time. And that's the key rule today. One change and then observe. Now, years ago when I started modeling antennas, I made a decision eventually to choose 5 degrees off the horizon as a benchmark. Not because 5 degrees is magic, it isn't, but because it's a realistic ballpark for general long-haul DX. And importantly, it gives us granularity, because if we benchmark antennas at 10 degrees, weaker designs can quietly get a free pass. They look fine because 10 degrees is a little bit easier to achieve, but 5 degrees, the truth starts to show. And that's why weaker antennas fall through the cracks. So 2 antennas that looked almost identical, this is what I found, at 10 degrees can suddenly be 3 or more dB apart when we force them to work down low. And that's the difference between the other station hearing you or not hearing you. Okay, so 5 degrees isn't a claim about propagation. It's a stress test, and it stops us lying to ourselves. All right, good. Now, just to ground this in reality for a moment, on HF, a single hop is typically somewhere around 2,500 kilometers. It's basically the longest hop we can achieve, depending on conditions. If our signal leaves our antenna at a high angle, we'll need more hops to get the same distance, okay, and hence greater path loss. If it leaves at a lower angle, you need fewer hops, okay? So every hop costs signal. So lower takeoff angles aren't about magic distance, they're about efficiency of the path. Fewer hops, less loss, better odds at being heard. Now, propagation is a huge subject, so let's keep it simple today. All right, we can start benchmarking and understanding what on earth is happening when we change sizes, heights, and length. And we're going to start with the simplest possible antenna, a plain quarter wave vertical over average ground, no tricks, no clever geometry. We'll benchmark it at 5 degrees, and then we'll remember that number. Then everything else we do, dipoles, loops, perhaps a Yagi if we get some time, has to justify itself against that. All right? So let's build our reference. This is MMANA. I'm just building a random vertical to say we'll do it for 40 meters. We'll keep everything at 40 meters. It doesn't really matter. So the height is going to be, I don't know, roughly 10.2. And wire 1. You don't need to know what I'm doing here. I'm just showing you that we've got a vertical here. It's sitting on the ground, all right? And I'm going to calculate it at 7.2 megahertz. It's giving us some SWR numbers, but that's not what we're interested in today. I'm only really interested in this bit, okay, which is a far field plot. So we can click some fancy numbers here, and we can have a look at what a vertical does over average ground. We've seen this in the books, haven't we? Whereas there's a hole right in the middle and our main gain is going out on the side, normally about 22 degrees. So this number here, which is, well, I'll go over that side, it's 22 degrees. So this line here, the outer line, is 0 dB relative to the antenna's strongest radiation. Everything inside it is how much weaker the signal is as we move away from that direction, okay? So it's not like the RF stops at this line. So the one on the left is showing us what it would look like, you know, for a bumblebee sitting above it. And the one on the right is the sidewalk, the pavement view as we looked at the antenna if we had our special glasses on. Okay, so, and I'm going to come down to 5 degrees off the horizon, which says minus 4.6 in this configuration. And all I've got is I've got a ground set up. I've said 24 radials, okay, and I've got some average ground for our country anyway. I mean, there's not going to be much in it, I promise you. What did we say? Minus? I thought it was going to be minus 5, but it's minus 4.6. Don't worry, there's a minus number, all right? We just want to remember minus 4.6, okay? And that's easy to do. All right, well, we can do some other things. We happen to know that a 40-meter vertical or dipole is resonant again at 3 and a bit times the frequency. So if we went to 21.7, I'm only going to 21.7 to get a nice SWR number. Don't worry about it. All right. It's the same thing. We can see that it looks a bit like a butterfly here. Our main gain is up around the top here, which is 45 degrees. But we can come down to 5 degrees off the horizon and do another measurement. Okay, 5 degrees minus 3. So in fact, we are 1.6 dB better off with a 3/4 wave, because you know the argument that a 3/4 wave is a bit of a cloud warmer, and it is up here, but we're still getting slightly better on this ground, okay? I'll do by the ocean in a minute. So I'm just going to reconfigure this for exactly 30 megahertz. You'll see why in a minute. I need this to be 6.25 meters long. I've done this so the maths is nice and easy, because 6.25 meters is actually a 5/8. So if I do the start button, ignore the SWR, this is our 5/8 pattern. Okay, so we can see now if we come down to 5 degrees off of the horizon, 1.7, 2.7, 3.7. So we're 3 dB better on a 5/8 as we were over a quarter wave. So let's get a bit longer. So that's 6.25. We remember 7.5. That would be our 3/4 wave again, look, which we had a moment ago. What happens if we go to a whole wavelength, which would be 10 meters long? We start to lose that low angle, look. And now we do get a cloud warmer. We'd need to match that with a transformer, okay, and do some clever stuff. But at 1.7 wavelengths long, which is 17.5 meters, okay, what does that do? We haven't got a bad SWR. And we got these little lobes down here, look. So let's have a look, coming up 5 degrees. So in fact, if I took one of my 18 meter poles and tuned it on the 10 meter band, technically I haven't got a bad takeoff angle there, look. Now, yeah, you get some, if you want to talk to the ISS, you're doing really good. But we're only measuring down here, okay? We could do an inverted L. Let's go back to, say, 7.2 megahertz. And we'll do an inverted L. We'll go up 5 meters. And then we'll go along 5 meters. So with the magic of the internet, let me just quickly speed up that. Right, we've now got an inverted L. This is up 5 and along 5. So roughly, if we go to, and tell this we're on to 7.2 megahertz, we'll get a rough match. It says 4.17 SWR. It means we're a couple of 100 kilohertz away, but it won't affect the far field plot. So an inverted L now starts giving us a little bit less of a hole in the middle, okay? In the main, you'll find that it's almost omnidirectional. So that's kind of verticals, which we might come back to in a minute. Now we can do a dipole, and we can do some clever stuff with a dipole. Obviously, we've got the height. We've got a shape, haven't we? It could be inverted V or whatever else. It could be a Z shape and so on. So let's just file new. So we'll do it for 40 meter band. So we'll do 10.5 one way and minus 10.5 the other way. It's a drawing function in here, but I know what I'm doing. So that's just lying on a piece of wire, lying on the ground. We need to put a piece of coax, wire one center. So if you remember the piece of coax, we've got the center conductor. That will go one way, won't it? Then the braid of the coax will go the other way. We'll need a choke, but it's just assuming we've got a choke in here anyway. So that's our red dot right in the middle. So now we can go and calculate this for 7.2. Add height. So we'll go really low to the ground. Okay, let's go, say, 3 meters above the ground. Ignore the SWR, right, very low to the ground here. And also there's a quirk of the maths that below a quarter of a wavelength above the ground, it can look a bit funny. But not the far field plot, okay? The far field plot is the interesting thing. So where is our Y? Y is north. So in fact, we're getting slightly more signal left and right, okay? And in the main, I think you would agree, that is a bubble of RF. There we go. It's, you know, there's not going to be much in it, right? So you hear about people saying, oh, I've got a low to the ground dipole facing north-south. And so obviously most of my signal is going east-west. In this case, yeah, a little bit, but not much. We could measure it, but on average, let's say if it was daytime, you wanted 45 degrees off the horizon. We have 7.4 there, 4.3. It's 3 dB in it. As we go a little bit higher, though, and we'll go to, say, 20-something feet, that becomes slightly more pronounced. Let's just keep it up. Let's go to a quarter of a wavelength off the ground. Looks like this. Let's go to 3, that's a quarter, 15 meters. So we can do half a wavelength off the ground. any dipole, half a wavelength off the ground, starts to look like this. Half a wavelength. So on 20 meter band, it'll be 10 meters high. A flat top dipole will give us this. So in two directions, 5 degrees, in two directions, we've got minus 3.5 one way and minus 3.5 the other way. So we are 1 and a tiny bit dB. You can't really hear 1 dB, all right? But technically, we're 1 dB over the edges, and we're minus 18 over here. So flat top dipole at a half a wavelength, right, is doing this. So we can get up to a full wavelength. That would be, on this case, it'd be 40 meters. On 20 meters, it would be 20 meters high. Maybe we should trim it back to 30. So 3/4 of a wavelength. What starts to happen? Well, we get this big bubble appearing here, which is no use to man or beast, but we don't care about the bubble. All right, we only care about our 5 degrees. So now we are 3/4 of a wavelength, and we've got 0 dB. So we are nearly an S point better here and here, but only here and here. We'd have to rotate it if we want to do something clever. All right, bear in mind the verticals all the way around. But that is for a flat top. I wonder what would happen if we made it into an inverted V. So with the magic of the internet, let me do that for you. All right, so we've built ourselves a traditional 40 meter inverted V, that coax going up to the middle. All right, this is 6 meters, 18, about 21 feet off the ground. The lowest the antenna reaches the ground is 1 meter. All right, so it's about up to here, you know. It's about 3 feet. So it's quite a low to the ground. We couldn't really get it much lower if we tried. And ignoring the SWR, we're not far out. It says 6.37. We can check this, by the way. We'll just quickly have a look. It says it's going to be around about 6.9 megahertz will be its sweet spot. It won't be. By the time we get out in the field and everything, you will have to adjust it anyway. But look, we're only after the far field plot. We can see now, do you remember if we find a frame, and I'll flick back to this, the flat top was north-south orientated, and we had a little extra gain west-east, didn't we? But this one, as you can see, is much more omnidirectional. So if I just 45 degrees, for instance, I think you would agree that is just omnidirectional. So if you've got an inverted V dipole at that size, I've always found it's omnidirectional. Okay, but we'll lift it up again. We'll do roughly, so we'll go to 40 feet, so it's about 12 meters. We did 10 meters before, didn't we? So the feed point will take it 10 to 10 meters, and we'll have a look at that. Now we can start to see a little bit of extra gain here, over here. You can see that by looking at the red dots going around here. 15. We did 15, didn't we? That's looking, 15 meters is pretty high. That's quite a big tree, actually. I've always found the biggest I can get a wire up anyway is about 20 meters, 60-ish feet. All right, looks like this. Now we can measure this one now. Minus 5.1. So in fact, our vertical will compete with this on transmit, you know, in 2 directions. So that's quite it. What else can we do if we had to come back down to low? I just want to give you some inspiration. 30 feet. Yeah, okay, let's do 10 meters. All right. If we made it like a Z shape, or if we did something a bit odd to it. So with the magic of the internet, let me just speed up and do this for you. Okay, this is the famous Z shape. I've actually done one of these in the past. And to be honest, I mean, the SWR is going to be a bit out. Where is it? Oh, it's gone high. It's around 7.4. It doesn't matter what the frequency is. I'm just trying to get a nice, there we are, get a match for you, just so you're not worried about this. So here's our Z shape. Now, how's this working out? So let's put Y at the top. Okay, so it looks like that, and that is the far field plot. Elevation 45 degrees, 5.7, 3.6. So there's 2 dB in it. So again, almost omnidirectional. And I say this because I had a shed shaped a bit like this in my attic. You see the current distribution, by the way, in blue is always off the centre on a dipole anyway. I didn't do that on the vertical for you, but you'll see that the current distribution, which is why it doesn't really matter what you do with the ends. The ends of the antenna, the last sort of 50% of the end, you can do all sorts with it because there's not much loss at the end. If you put a coil right near the feed point, all the loss will be running through that feed point. Let me just show you the current distribution on a vertical. So here's the current, right? You can just see that the current distribution is coming. You can see the big, all right, well, you can see that current distribution. Most of the RF is on the base, and you can kind of see why you need a good ground, right? Because 1/2 of that antenna is literally the ground, okay? And if we went to the ocean, and I can, to the ground setup, is that in terms of millisiemens per meter, if we're right on the beach, okay? Not in the sea, all right? Just right by it, okay? Our vertical now starts doing something really, look at this. 5 degrees is 4.2. So we are, they say it's like having a 10 dB amplifier if you're by the ocean. So if we went to 21.7, we could change the size, okay? And look at the current distribution. Now we'll see that you can literally see 3 quarter waves, all right? And how that top 2/3 looks like a dipole. And but by the ocean, we're by the ocean right now. We haven't got quite as much gain as, funnily enough, we have on the vertical quarter wave. So anyway, that was a little throwaway. All right, so we've done verticals. We've done an inverted L. We've done the dipole and various shapes. But anyway, we were looking at this low angle, weren't we? All right, just to, what happens. That basically we need a bit of height if we're on a dipole, or we need, the best ground we can get if we're on a vertical. Right, so now let's go to a loop. Just drawn a nice little loop antenna. It looks like this. We have, it's flat to the ground, horizontal at the moment. We have a feed point in one corner with a 4-to-1 balun on it. And I'm looking at just maybe 3 meters, maybe 2.5 meters, so about 8, 9, 10 feet off the ground. And we can see, like any low to the ground antenna, right, we get this lovely daytime, this is for 40 meters, lovely daytime antenna, very strong on the way up. So what I'm going to do is I'm just going to increase the height to 10 meters on the 40 meter band, and we can see nothing really change. It is still very much omnidirectional. Now, whereas a dipole is every other harmonic, okay, it doesn't resonate on the next harmonic, it resonates on the one after, all right? So that's why on HF, the only 2 bands that are useful to each other is 40 and 15. By the way, there's a trick on the 15 meter band on a dipole. If you fold the end over about 6 feet, you'll find, with a bit of tuning, you'll end up with 40 and 15. Perfectly. Same with a vertical and a dipole. Right. Now, because this is now resonant on, it'll be roughly about 14. We can look at the far field plot and how that changes. This is quite high now, but 3, appropriately looks like this, 10 meters high. We've got a little bit of gain here and there. So if we go to our 5 degree off the horizon, just see what if we're beating our, yeah, we are. We're beating our vertical in that direction. It's opposite the feed point. About the same behind us. Not quite as good top and bottom. That was 20, but we'll get 40, get the 15 meter band as well. Look, 20, I don't know, 0.35, whatever. And we start to get this rather nice pancake. I don't know why we get a pancake on 15, but anyway. So we've got this tremendous antenna. We're about 5 to 6 dB better than our reference, which was our vertical originally. And it beats everything and almost omnidirectional. That's what the plot looks like. Lovely, isn't it? And if we go up again, it will be resonant on 28 point, I don't know, 5. Have a look at that. And opposite the feed point is over here at 5 degrees off the ground. We've got 5 dB. Okay. So 10 dB, that's like going from 100 watts to 1,000 watts on transmit and receive, actually. We've got 10 dB receive here, 11 nearly, opposite the feed point. So we're beating, this clock face looks absolutely wonderful, doesn't it? Show you a pretty colour. Looks like this, a bit weird. But this is this big red piece. Whoops, I'm upside down, left and right. This big red piece is the opposite the feed point. Interesting enough. We'll convert this to a vertical in a minute. A vertical delta loop is really a monoband, and I'll show you why. Let me just rescale this from 7.2 to 3.6-ish, you know, whatever. Doesn't really matter. So 10 meters again. So we'll still get, we're on 80 meters now. Lovely little antenna. Low to the ground, by the way, all these don't really perform. That's minus 12. It's too low. If we go to 40 meters, 7.25. 5 degrees. Minus 7.8. But can you see this bubble here? It's quite interesting how it produces. 14.25. We've now got .6. So if you, what height are we here? Only 10 meters off the ground, but we've got an 80 meter loop up triangle opposite the feed point. You know, if that was Europe, for instance, and you in the US, it's minus 1.6. That's pretty good, right? That's pretty good, not nice bit of gain. But if the band's open, 21.3, whatever. Now here is 15 meter band. We've got basically 10 dB starfish, isn't it, really? Well, it's a hexagon. It's a hexfish. And 28.5. .1 dB. I mean, it's an insane amount of... if you can just find 3 trees in the right place. However, we built one of these down at the Scout Hut years ago. Let me just resize this for, I don't know, it was 158 meters, I think. 1.9 top band, give or take. 40 meter band. And we had ours on, it was 20 meters high, about 60 feet. 3 big oak trees, just so happened. Ignore the SWR. I could start tinkering with it, but that's not the point. 5 degrees off the horizon. Minus 2.1, so we're 3 dB better on the 40 meter band. Incidentally, on 80 meters, it'll just be fairly NVIS. Okay? Do you remember that plot? We had that on 40 a minute ago. But let's have some fun. Let's go up to 14, up to 20 meters with a, we call this a mega loop. No, I made a video about it a while ago, but mega loop. There we are. Look at this. So I was running a pile up with the amplifier on, and I came, and that was this heading here, this 20 degrees, was basically covered most of North America for me, all right? And by the way, that is saying 8.9 dB, 9 dBi, so we're nearly 15 dB. I mean, it's a phenomenal amount of gain. And I wound the power down to either 5 or 10 watts, and I was still holding a pile up to the US, because that sort of gain is very difficult to achieve on HF. Just a quirk, isn't it? Just a quirk. I mean, we could do, just for fun, 15 meters band, 21.35, just for fun. Whoops. Right. So look at all these. So a friend of mine, we used to go down the Scout Hut, take my big amplifier, and we would call CQ. On any band, you know, someone inevitably, no matter what the band conditions were doing, would inevitably get back to us. Okay, so remember that -5? It was just a good... and by the way, -5 at 5 degrees still gets you around the world, right? But you just bear in mind that if you want a dipole, you need to get it up a bit higher. So the magic of the internet, I'm going to attempt to make this thing vertically polarized. Just hold on a minute. All right, so let's take this height back down to 2. So this is a vertically I spent a ton of time organising this SWR, and I've changed the height and it's changed it. It doesn't matter. It won't adjust the far field plot. So they say, if you look at ON4UN book, put your feed point a quarter of a wavelength down from the top. Okay, and what we end up with, if you think about it, is a pair of it's a phased array. If we took the currents and zoom these currents, we'll see that it's starting to look like a pair of dipoles, a pair of verticals in a funny sort of way. Right. So, but let's have a look at the far field pattern. Bearing in mind we are north-south, so X is through the middle. And here we are, through the middle. So this is a vertically polarized delta loop, 5 degrees off the horizon, -4.1. So we're only a dB more than a single vertical on exactly the same ground, by the way. I haven't changed the ground. And how high off the ground are we? So we're quite high. So the top of this thing, right, is, take that one there. The top is 12, 13, 14, getting on for 50 feet off the ground. So that most people would have this, if they're lucky, that's about 3 feet off the ground. It looks like this. Oh, there's a quicker way of doing this. So yeah, we're a dB better. You would have to get this way off the ground. So, I mean, I didn't know that actually. 5 meters off the ground. I mean, this is really maybe hanging off your tower or something. And if you've got a tower, you might as well put a Yagi up anyway. Elevation 5. Yeah. That is which direction is that? And we could invert this. You know, we could have it so that it's completely the other way around. But that traditionally is the way of getting gain out of a delta loop. But this is with a 100 ohm feed point, so it's with a quarter wave matching section, not a 4-to-1 balance. And that's why 14.3 or something. I mean, we will get a match, but the pattern looks really nasty, you know. I mean, it's not even very good off the ends. It's a monobander, okay? So anyway, I feel I'm running out of time, actually. So, yeah, I think I've been going long enough. Okay, so now I've deliberately left off end fed, and I'll tell you why. It's because it's not that they don't work. It's some of them do. It's particularly on the lower bands for general HF work, but I left them out in my mind, to be honest, because they introduced too many variables for this kind of comparison. Overall lengths, heights, shapes, feed arrangements, common mode choking, feed point height, is it inverted L, is it straight? Huge influence on particularly the upper HF bands for the pattern, okay? So for a talk about isolating height and radiation, they muddy the water a little bit, in my opinion, right? I just wanted to sort of clean the geometrics with predictable behaviour. And to say that let's really think about this, right? And pull everything together. We've looked there, therefore, okay, we've looked at three very different antennas, a vertical, a dipole, and a loop. Now, they look different, they're built differently, and we've changed the heights, the sizes. We've just given you a fair idea about roughly what happens when you change it. But electrically, they're all doing kind of the same job. What separates them isn't magic. It's not efficiency either, right? It's just the radiation angle, right? The vertical excels at producing low angle energy everywhere. As they say, it kind of follows the propagation, especially when the ground helps it. All right. When I say when the ground helps it, you can get fantastic gain by the ocean. It'll still work, not by the ocean. All right. The dipole gives us flexibility because during the day, a low to the ground dipole for the low bands is fantastic for NVIS. It gives us, all that. But it can't do DX and NVIS at the same time, right? Now, the loop rewards size and height, okay? Once it's big and high enough, it can produce some really amazing, surprising gain on the higher bands. It's great fun. Find yourself 3 oak trees and a catapult. What's important, right, is that none of these antennas are good or bad. Right? They're kind of honest, right? They do exactly what their geometry and height allows them to do. Most frustration in amateur radio doesn't come from a bad antenna. It comes from using the right antenna at the wrong time, or the other way around, or expecting one antenna to do everything, right? So daytime on 40 meters, a low dipole, a low loop, happy days. Dawn, dusk, night, maybe longer paths opening up. Now low angle is required, right? Right, and that's where the vertical or something higher up begins to win, doesn't it? And once you understand that trade-off, antenna choices start to become more calmer, right? It's more kind of situational, right? Now, before we finish, I want to touch on something that causes a lot of frustration on the low bands, noise. There's an old saying in amateur radio, it always makes me laugh. If I can hear them, I can work them. And I always wonder, what happens about the station you can't hear, all right? So on transmit, we are capped. In the main, we've got a 100-watt radio, and 100 watts is 100 watts. So the physics is firmly in charge. On receive, the loops are a tiny bit different. Most modern radios give us, I don't know what it is, 15 or 20 dB of gain on the receives, on the press of a button, the preamp button. Right? That's enormous. Now, we can't invent signals if they're not there, right? But if they're slightly buried, we've got some choices, haven't we? And you've probably noticed this one, that long wire in the trees or the odd bit of wire you clipped on for a test. It tunes on 80 meters, but reception is hard. Everything's buried, in the mud. The problem isn't that the antenna is so much inefficient. The problem is often the noise. And that is why the receive socket on the back of your transceiver, I'm thinking the 7300 Mark II, TS590 SG and so on, is gold. I'm surprised how rarely people use it. Just one more economy run of coax out to the trees. Now you can transmit on your main antenna, the one that handles efficient power and low angle and everything else, and listen on something completely different with the preamp engaged that is out the way of the noise. A loop on the ground, a short dipole on the ground. On receive, efficiency doesn't matter as much. Quietness does. And once the noise floor drops, the signal appears. Once the signal appears, well, we can add gain. So suddenly stations that simply didn't exist before are workable. I was personally astonished how well a small 15-foot square loop on the ground, what's that, 3.5, 4 metre square, all the way around. And it works all the way down to 160 metres. Fabulous on the shortwave bands. Just general reception too. I want to leave you with a couple of practical observations. These aren't rules. They're things that I've learned the hard way by breaking, well, a lot of stuff, right? And rebuilding antennas over the years. None of them require exotic materials, right? Or big budgets, about avoiding what I call the common traps. Now, wire choice rarely matters for antennas. It just needs to be strong enough to survive the weather and the tension. Anything. I've used just about every type of wire you can possibly imagine, and I've never been able to hear a difference, okay? Coax does matter, right, to an extent. If you need to use RG58, use it for short pigtails, not for long runs. Lossy coax doesn't just lose signal, it introduces noise too. I like to use the term bleeding, because it's just not got a good enough screen. So good coax is worth more than any exotic wire. And finally, if an antenna sounds noisy, it may not be broken. It may simply be doing exactly what you asked it to do, picking up low angle energy. So the crud poking through from next door neighbours. Fairy lights, well, join the dots. So there's no best antenna. There's only one antenna that suits this band at this time over this ground. And once you understand radiation angles, antenna choice stops being mysterious. It becomes situational. It's horses for courses. So have confidence, be bold, and use this knowledge to grow your own understanding of radio science. It doesn't need to be complicated, all right? Enjoy your radio.